Welcome to Spring LIB.
So here's a diagram of what the situation looks like. So initially the wheel is around here where the rotational velocity of the wheel is 25 radians per second. Then it starts rolling upwards and it reaches till height h where the rotational velocity becomes zero because there's gravity acting on it. So that's why it can reach up to a certain point. So to solve this problem, we'll be using conservation of energy, and because there are various ways to solve this problem, but I guess this is one of the easiest ones. So that means we need to find out the total energy stored here, and then we need to find out the total energy stored here. And since energy is conserved, so we'll just equate these two parts of the energy, and then we can solve for the height. Now let's call this point number one, and let's call the other one point number two. So that means at here we'll have kinetic energy k1 plus potential energy u1 plus some other form of energy here. The other form of energy is the frictional force. Then at this point we'll have kinetic energy and potential energy. And also, as you can see, we are taking the center of the wheel as the origin here. So that means y is 0 here. And the height is basically from the center of wheel at this point to the x-axis. Right. Um, so now if we write the kinetic energy, we see that kinetic energy has both translational and rotational motion because the wheel is rolling as well. So we'll have kinetic energy equal to half of ICM, where I is the moment of inertia. Then we have omega squared plus half m PCM squared. So V is the linear velocity and this is the angular velocity. Now, as we mentioned this, so I just wrote down the equation over here as well. So that's the kinetic energy, and that's the energy conservation equation. Now, what we're given is the other form of energy, which is 2600 joules. Now we're taking negative sign here because we know that work done due to friction is negative. So we have a negative sign. So that's this other form. Then K1 at point 1 is I times omega 1 plus half of m times V1. So V1 and omega 1 are the linear velocity and rotational angular velocity at point 1. And we can know, since the wheel is rolling without slipping, we can use this relation right here where V is equal to R times omega. Also, we're given the uh, moment of inertia, so we can directly use that. So if we put all this together, we see that K1 is 0.9 mr squared omega 1 squared. So we just shrunk our expression in terms of m, r, and omega 1. Now, at point 2, since the wheel stops, that means there is no kinetic energy there. Oh, and also there's no potential energy at point 1 because we're considering y equals 0 at here. So that means the potential part goes away, and here the kinetic part goes away. So all we have is the potential energy. So the potential energy will be m times g times h, which is the gravitational potential energy. So we'll just equate these two parts. So we have the kinetic part, we have the other form of energy, and then we have the potential part. And we know that we are given the weight of the wheel, so we figured out the mass by dividing the weight by gravity, which gave us 40 kilograms. So if we solve for h from there, we'll have this expression. So we just divided mg by this whole thing, and that's what we got as h. And we're given all the values like mass, radius, omega 1, or rotational uh, angular velocity, and the other form of work done, which is the work done due to friction. And if we plug in all those, and remember there's a negative sign, so this will be negative while putting this. If we plug in all those, we get the height as 14 meters. Thank you.